Hello viewers, welcome to this next session on the stereochemistry of carbon compounds. In our today's session, first we will discuss what we have done in our last session. Then next we take up the compounds which contain more than one asymmetric carbon atom. We will discuss that how many stereoisomers are possible in such compounds. Then we will talk about diastereoisomers and mesocompounds. After that, we will talk about elements of symmetry. Then we will take up some compounds which are optically active and they do not contain any asymmetric carbon atom. Finally, we will summarize our today's work. In our last session, we had discussed about compounds which contain a chiral center. This is a molecule that you are looking at. This is a carbon with 4 different groups attached to it, and its mirror image is there which is non-superimposable over it. We had discussed that such compounds are called chiral compounds, and such a pair of isomers, they are called enantiomers. Enantiomers are non-superimposable mirror images of each other. Out of these 2 isomers, one isomer is dextrorotatory and other is levorotatory with the same magnitude of rotation, and mixture of these enantiomers is known as racemic mixture. Then we had discussed about the chirality. Chirality is basically non-superimposability of mirror image. It is a necessary and sufficient condition for a molecule to show optical activity and hence the optical isomerism. This is what we discussed in our last session. We also discussed that compounds which contain one asymmetric carbon atom, then in those cases only 2 isomers are possible. One will be dextrorotatory and other is levorotatory. We have come across 3 terms in our previous session. One is asymmetric carbon atom, other is chiral center, and third is stereogenic center. Actually, these 3 terms are used interchangeably. Asymmetric carbon atom means a carbon which has 4 different groups attached to it. If such a carbon is present in a molecule, then molecule becomes chiral and hence it is called chiral center. And since due to this the stereochemistry is generated in the molecule, so this is also called stereogenic center. So these 3 terms can be defined in one sentence like this, that a carbon atom carrying 4 different groups is known as asymmetric carbon atom or a stereogenic center or a chiral center. Now today we will discuss about the compounds which have got more than one asymmetric carbon atom. How many isomers are possible and whether all of them are optically active or not. It has been observed that maximum number of possible stereoisomers for a compound containing more than one asymmetric carbon atom is 2 raised to the power n, where n is the number of asymmetric carbon atoms. Means if asymmetric carbon atom is 1, so 2 raised to the power 1 means 2. So only 2 isomers are possible. This we have already discussed. Now if there are 2 asymmetric carbon atoms, then the maximum number of possible isomers become 2 raised to the power 2 means 4. Similarly, if a molecule contains 3 asymmetric carbon atoms, then the maximum number of possible stereoisomers will be 2 raised to the power 3, that will be 8, and so on. Now let us study it with the help of an example. The example is 2-bromo-3-chlorobutane. This is the structure for 2-bromo-3-chlorobutane. Star shows on these 2 carbons that these are 2 asymmetric carbon atoms. This is a carbon which has 3 different groups attached to it, 1 methyl, 1 hydrogen, 1 bromine and 1 remaining part of the molecule. Whereas on this carbon also there is 1 hydrogen, 1 methyl, 1 chlorine and the 4th group is the remaining part of the molecule. Since this molecule contains 2 asymmetric carbon atoms, so number of possible stereoisomers is equal to 4. Let us see these 4 possible isomers with the help of models. This is one structure in my hand. In this model, these black groups, they indicate methyl groups, and these white, they indicate hydrogen. Red is indicating a bromine, and this blue group is indicating a chlorine. See, now this is one molecule in my hand which has bromine and chlorine on the same side. Then another is its mirror image. See, in the mirror image that bromine and chlorine are opposite, hydrogens are going outward, and then methyl groups are coming behind. Now let us try to see that whether they are superimposable or not. I try to put one model over the other, and I find that they are non-superimposable, because if methyl and methyl, they are matching, these hydrogens and bromine or chlorine are not matching with each other. If I rotate it and try to match these hydrogens, then this region overlaps, but this methyl and bromine or methyl and chlorine, they are not overlapping. It means these two molecules in my hand, they are non-superimposable over each other, and they are mirror images. They are made up of same atoms. It means they are enantiomers. So it means this is a pair of enantiomers. Let us talk about another possibility. When this bromine and chlorine are across and two hydrogens are across. This is one possible structure, and then there is another structure in my hand which is its mirror image. Again, if we try to superimpose these two, what I find that they are non-superimposable. If these methyl groups are superimposing, these hydrogens and bromine and chlorine, they are not superimposable. If I rotate and try to superimpose hydrogens, even that is not feasible, because now two chlorines are matching, two hydrogens are matching, but these methyl and bromines, they are not matching. It means they are also non-superimposable mirror images of each other. It means now for 2-bromo-3-chlorobutane, we have these 4 possible isomers which constitute 2 pairs of enantiomers. Let us see these 4 possible isomers in Fischer projection also. This is the Fischer projection. This is first isomer where bromine and chlorine are on the same side, and then its mirror image. They constitute 1 and 2 enantiomers. Then there is a third when bromine and chlorine are across. They also constitute another pair of enantiomers. Now all these 4 isomers are of the same compound 2-bromo-3-chlorobutane. We have shown a relation between 1 and 2 as enantiomers. Similarly, between 3 and 4 as enantiomers. But what is the relation between 1 and 3 or 2 and 3? Similarly, 1 and 4 or 2 and 4. They are also the isomer of the same compound. So these isomers have been given the name as diastereoisomers. So this pair 1 and 3, 2 and 3, 1 and 4 and 2 and 4, such pairs are called diastereoisomers. Diastereoisomers are defined like this, that they are the pair of stereoisomers which do not have mirror image relation with each other. So it means for any compound we can have different stereoisomers and we can distinguish them as enantiomers or diastereoisomers. Enantiomers are the pair which are mirror image of each other and non-superimposable. Diastereoisomers are the pairs which do not have mirror image relationship. Means they differ in the arrangement of groups in such a way so that they do not form each other's mirror image. Diastereoisomers, they differ in their physical properties, whereas enantiomers have all their physical and chemical properties identical. They differ only in one property, that is called optical activity, whereas diastereoisomers differ in other physical properties also, like solubility, melting point, boiling point and so on. And this difference in their physical properties help in the separation of diastereoisomers also. Now, if we compare here the geometrical isomers which we had studied earlier, we said that geometrical isomers are also non-superimposable and they also did not have any mirror image relationship, cis and trans isomer of any compound that we have discussed earlier. So, those geometrical isomers are also classified as diastereoisomers. Means cis and trans isomer of a compound also constitute a diastereoisomeric pair. Let us take another example, tartaric acid. Now, tartaric acid is different from 2-bromo-3-chlorobutane in a way that the two substituents at the asymmetric carbon atoms which were different, here they are same. Means each asymmetric carbon atom in this case has got one hydrogen, one hydroxyl and one carboxyl. Similarly, the other asymmetric carbon atom also has one hydrogen, one hydroxyl and one carboxyl. So, we are taking this as a special case. This is one isomer that I have written. There is another isomer which is its mirror image. We will see it with the help of models that whether it is superimposable or not. And there is a third isomer in which we put both the hydroxyls on the right side, and we will see with the help of model that this mirror image is identical to it. Let us see now these molecules with the help of models. This molecule is representing tartaric acid. Now, remember that this black group represents the carboxyl group, these white groups they represent the hydrogen atoms, and this red group they represent the hydroxyl group. So, I have one isomer in my hand in which the two hydroxyl groups are across. Then there is another model now which is its mirror image. Now, let us see whether they are superimposable or not. When I put this over it and try to superimpose, I find they are non-superimposable, although they are mirror images of each other. So, it means these two molecules in my hand are enantiomers. They are mirror image of each other, but they are non-superimposable. It means obviously they will be optically active. So, for this tartaric acid, I have these two optically active isomers. Then another possibility, when the two hydroxyl groups are on the same side and two hydrogens are on the same side. This is its mirror image. Now, when I try to superimpose these mirror images like this, I find that they seem to be non-superimposable. But if I just turn it over and now I try to superimpose, I find that they are superimposable. Means these two models in my hand, they are representing the same molecule. They are not the enantiomers. Although as we have made the models, they are mirror image of each other, but these mirror image of each other are superimposable. It means they are representing one and the same molecule. So, for tartaric acid, it shows that there are three possible isomers. The two structures which we have written, they are identical. These two isomers are superimposable over each other and hence they represent the same molecule. So, it means for tartaric acid, three isomers are possible, out of which two represent a pair of enantiomers that we have seen earlier. So, they will be optically active. Since in this case, this molecule and its mirror image, they are superimposable, it means they will be optically inactive, right. So, for tartaric acid, four isomers are not possible, three isomers are possible, out of which one is optically inactive and two are optically active. Whereas for 2-bromo-3-chlorobutane, which we discussed earlier, the four isomers were possible and all four are optically active because they are representing two pairs of enantiomers. In tartaric acid, I am repeating, one isomer is optically inactive and only two isomers are optically active. Such compounds which are optically inactive, let us see the structure again. What we find in this structure, that this dotted line that is representing a mirror plane and we see carefully that across this line, this part of the molecule is exactly the mirror image of this part. Means this asymmetric carbon atom has 4 groups, 1 hydrogen, 1 hydroxyl, 1 carboxyl, and remaining is this part of the molecule, whereas this carbon also has got 1 hydrogen, 1 hydroxyl, 1 carboxyl, and remaining is this part of the molecule. So it means the substituents on each of these asymmetric carbon atoms are identical and one half of the molecule is mirror image of other half. So that molecule becomes optically inactive because whatsoever effect is caused by one asymmetric carbon atom on plane polarized light is exactly cancelled by the other part of the molecule. Such compounds are named as meso compounds, where one of the molecule is mirror image of the other half. These meso compounds are optically inactive and cause for their optical inactivity is internal compensation. Internal compensation means internally one half of the molecule is compensating the effect caused by the other half. Racemic mixtures we discussed in our last session were also optically inactive, but there the cause of optical inactivity was external compensation, because half of the molecule are causing the rotation in one direction and other half in opposite direction. Whereas in this case, one half of the molecule is causing a rotation, the other half of the molecule is exactly cancelling each other. So this third isomer of tartaric acid is called meso isomer. Now we have discussed till now that for a molecule to show optical activity, chirality is required. But how do we check chirality in a molecule? We have discussed that a substance is chiral if its mirror image is non-superimposable over it. In case of smaller molecules also, we have seen that we can do it with the help of models. We can make the model of one isomer, then make the model of another isomer. We try to superimpose these two models and then we can say that whether they are superimposable or not. But the things become difficult when number of asymmetric carbon atoms are increasing in the molecules. Means if the molecule is of larger size, then it will be very difficult to construct a model, then construct a model of its mirror image and then check the superimposability. Then how should we do it? For doing this, we look for some elements in molecules which are called symmetry elements. We look for some basic symmetry elements in molecules. It has been observed that if some of these symmetry elements are present in a molecule, then its mirror image will be superimposable and this will be achiral. And if any such symmetry element is absent, then molecule may be chiral. Let us first discuss briefly these symmetry elements that we use in organic compounds. One of them is center of symmetry. Center of symmetry is defined like that it is a point in space such that if a line is drawn from any part or atom of the molecule to that point and then extended an equal distance beyond it, an analogous part or atom will be encountered. Let us understand with the help of this structure. This is a molecule which is a cyclobutane derivative. It has got 2 carboxyl groups at these 2 positions and then 2 methyl groups at these 2 positions. We see that if we draw a line from this carboxyl, it is passed to this point and then extended beyond, we meet another carboxyl group after the same distance. Similarly, if I start from this hydrogen and move to this point and then extend this line beyond it, we will meet another hydrogen. Similarly, for methyl group, we find that after an equal distance passing through this point, we get a methyl group. Such a point in a molecule is called center of symmetry. Center of symmetry is also represented by small I. Let us see it in some other molecules also. This is a heterocyclic molecule in which nitrogens are there as a part of the ring. Still we see that this has this point as a center of symmetry. If I draw a line from this oxygen to this point and then go down the plane, we will meet this oxygen. Similarly, if we start from this methyl, pass to this point, we meet methyl here. So we say that this molecule has got a center of symmetry. Then there is another molecule, that is a mesotartaric acid we discussed just now. We see that if I start from this carboxyl group and pass through this point and then go beyond, I meet another carboxyl group, or if I start from this hydroxyl group, line is drawn up to this point and extended, we get another hydroxyl group. So this molecule also has center of symmetry. So in this way we can check the presence of center of symmetry in different molecules. If a molecule possesses a center of symmetry, we will talk about it little later, then what will be its effect. Second element of symmetry is plane of symmetry. A plane of symmetry is a plane such that if a line from any element on one side of the plane is drawn perpendicular to the plane and the line extended to an equal distance on the other side of the plane, an identical element is found at the end of the line. In other words, we can say that one half of the molecule is mirror image of the other half. This is again the same thing that we have discussed just now in case of mesotartaric acid. This is again mesotartaric acid, and this is the plane where we find that if we put a mirror here, this half of the molecule is mirror image of this half, although these two are chiral centers, that is asymmetric carbon atoms present in the molecule. We see the same molecule we have seen earlier in Fischer projection also, because that is a planar representation. This represents a mirror plane and one half of the molecule is mirror image of other half. We find this plane of symmetry not only in organic molecules but many objects that we see around, like a simple butterfly. We see that in this butterfly, one half of the body and the wings is identical to the other half. Similarly, a very famous monument, that is Taj, that is also very symmetrical. One half of the monument is symmetrical to another half. So these lines which have been drawn here in red color, if we put a mirror here, we will find that one half of this monument will be mirror image of the other half, or one half of this butterfly body part will be exactly the mirror image of other half. So there are many other objects also we see which contain a plane of symmetry. Then next is alternating axis of symmetry. Alternating axis of symmetry is also known as improper axis of symmetry or also rotation reflection axis of symmetry. A molecule is said to possess an n-fold alternating axis of symmetry if rotation through an angle of 360 by n about this axis and then followed by reflection in a plane perpendicular to the axis gives a molecule which is indistinguishable from the original molecule. Now let me explain what do you mean by n here. N figure comes that suppose a molecule is rotated by 90 degrees and then we get whatsoever has been explained here, then value of n will be 4. Suppose we get this type of observation after rotation of 180 degrees, then value of n will be 2. So we say that a molecule possesses a 2-fold alternating axis of symmetry or 4-fold alternating axis of symmetry, or this thing is observed after rotation of 60 degree, then we may say molecule possesses a 6-fold alternating axis of symmetry, and so on. Then what do you actually see in this alternating axis of symmetry? As it is mentioned here, that first we will find an axis, we will rotate the molecule by some angle on that axis and then we will get a reflection in a plane perpendicular to the axis. Means we will take a mirror which is perpendicular to this axis and take the mirror image. If that mirror image is identical to the original molecule, then we say that molecule possesses an alternating axis of symmetry. Let us understand this thing with the help of an example. Say this is a molecule which is cyclobutane derivative and has got this hydrogen and carboxyl group and phenyl group etc. as substituents. We find that similar type of groups are across, means we will not be able to get the position for the similar group by rotation across 90 degree. So we try 180 degree rotation. So after a rotation of 180 degree, we get this situation. This is the axis where this S2 is written. We find that after 180 degree rotation, this corner, it comes here, it becomes this corner, and this corner, this becomes this corner. So this phenyl and H which were here, they are now visible here, and similarly this phenyl and H, they have gone there. Phenyl is below the plane, H is above the plane. Similarly this carboxyl and hydrogen, they have come to this position. Carboxyl is above, hydrogen is below, and these hydrogen and carboxyls have come to this position, hydrogen above, carboxyl below. So we have obtained this situation after rotation across 180 degree. Now we have to see the mirror image of this situation across a mirror which is perpendicular to this axis. Means here is the mirror, and let us see what do we get as its mirror image. So if this is the mirror image of this molecule will be this, it is under. The carboxyl which was going above will be going down here, and this carboxyl which was going down will be above the plane. And now if I compare this structure with our original structure, what we find? We find that they are exactly identical, they are matching. This CO and H, this COH and H, this phenyl H, this phenyl H, and so on. So means what has happened? We had a molecule, we rotated it across this axis by 180 degree, we got another situation, then we took a mirror at a 90 degree angle to this axis and got its mirror image. We find that mirror image is identical to this. So this molecule is now said to possess an alternating axis of symmetry. But how many fold? We are getting this thing after a rotation of 180 degrees. So it is said to have a two-fold alternating axis of symmetry, and it is generally represented as S2. Let us take another example. This is 1, 2, 3, 4 tetramethyl cyclobutane, but that particular isomer which have these methyl groups alternately above and below the plane. Now here we may try the situation by rotation across 90 degrees. So we rotate it by 90 degree and we get this situation. This carbon where methyl was above, after rotation of 90 degree across this axis will occupy this corner, means here. So this is methyl above and hydrogen below. This corner shifts to next, that is hydrogen and methyl above and below. Then this corner shifts here, that is methyl and hydrogen above and below. Now let us take the reflection of this across this mirror which is perpendicular to this axis. Now we get this situation. This is the mirror image of this across this mirror. Hydrogen was going above, methyl was going below. In the mirror image we will find that methyl is going above, hydrogen is going below, and same will be the situation for substituents at all other corners. And now what we find? That this particular structure and this structure, they are identical. So means by rotation across some angle across an axis, we got another structure. Then we get a mirror image of that structure in a plane which is perpendicular to that axis. Whatsoever we get, if it is identical to after original molecule, we say that this molecule possesses an alternating axis of symmetry. So in this case now we are getting the situation after a rotation of 90 degree. So this molecule is said to possess a four-fold alternating axis of symmetry. So now till now we have talked about three symmetry elements: center of symmetry, plane of symmetry, and alternating axisymmetry. It has been observed that if a molecule possesses any of these symmetry elements, its mirror image will be superimposable and that molecule will be achiral, that molecule will be optically inactive. There is another element of symmetry which is called simple axis of symmetry. A molecule may possess simple axis of symmetry or not, it has nothing to do with the chirality of the molecule. But after all, it is a symmetry element. It is also called symmetry axis. Let us take an example. It is defined as an n-fold axis of symmetry is an axis such that when a structure possessing this axis is rotated by an angle of 360 degree by n around the axis, the structure which results is superimposable with the original one. So, difference between simple axis of symmetry and alternating axis of symmetry is that in simple axis of symmetry we rotate the molecule by certain angle around that axis and we get the identical structure. Whereas in alternating axis of symmetry we rotate it by certain angle around the axis and whatsoever get its mirror image perpendicular to that axis is identical to original structure. This is the basic difference between these two. Let us take a molecule. This structure is there where we find that this is the axis and when we rotate by 180 degree around it, we get identical structure. Another molecule, this is the axis, when molecule is rotated around this axis, we get identical molecule because CO goes there, NH goes there. So, such molecules are said to possess simple axis of symmetry. Now, if a molecule contains some element of symmetry out of the plane of symmetry, center of symmetry and alternating axisymmetry, those molecules were called symmetric molecules, and if they were absent, then earlier the name was given as asymmetric molecules. But asymmetric molecules, suppose it contains simple axis of symmetry, then these symmetry designations are slightly changed now. We say that a molecule is symmetric, simple axis of symmetry may or may not be present, but alternating axis of symmetry is present. Now, here one more thing I would like to add, that one fold alternating axis of symmetry correspond to plane of symmetry. Means a molecule which possesses the plane of symmetry will have one fold alternating axis of symmetry, and two fold alternating axis of symmetry corresponds to center of symmetry. So, only symmetry element about which we can talk in terms of alternating axis of symmetry. So, if alternating axis of symmetry is present, molecule will be optically inactive. Such molecules are called symmetric. If alternating axis of symmetry is absent, simple axis of symmetry is also absent, we call those molecules are asymmetric and they are usually active. But if simple axis of symmetry is present and alternating axis of symmetry is absent, then such molecules are now given the name as disymmetric and they are usually active. Then there are some other molecules which do not contain asymmetric carbon atom, but still they show optical activity or optical isomerism. One group of compounds are allenes. Actually, in these compounds they do not have a chiral center, but there is a chiral axis that is shown by this dotted line, and we call this as a stereogenic center in the term of this axis. Similarly, in case of biphenyls, this axis also is there, due to which molecule acquires this stereochemistry. In both these cases, these groups are not able to cross over each other and they give rise to stereoisomerism. So, this is all about the optical isomers. Today, we have first reviewed about the enantiomers that we had discussed in the previous session. Then we discussed that how many isomers are possible with compounds containing more than one asymmetric carbon atoms. We talked about diastereoisomers and meso compounds. I will repeat here that meso compounds are those compounds where one half of the molecule is mirror image of other half. Then we discussed about the elements of symmetry, and if a molecule possesses any of these elements of symmetry, that is center of symmetry, plane of symmetry or alternating axis of symmetry, this molecule will be optically inactive. Such molecules are achiral molecules. And then last we have seen briefly the compounds which do not contain asymmetric carbon atom, but still they are optically active. In our next session, we will talk about the nomenclature that is given to the configurations of these optical isomers, and we will also